Equation-1 solves linear harmonic oscillator problem quantum mechanically. One encounters a differential equation known as Hermite differential equation. The equation is y double prime minus twice x y prime plus alpha y is equal to 0. Clearly, any finite x is a regular point of this differential equation. Any finite x is an ordinary point of this differential equation. So, the region of interest where we should apply this equation extends from minus infinity to plus infinity. If you consider an harmonic oscillator, then the amplitude of the oscillator, if we write classically the amplitude as A cos omega t, then this amplitude omega A is related to the energy. The greater the energy, greater is the amplitude. So, as we go on increasing the energy of the oscillator, the amplitude will go on increasing. So, it is reasonable that this equation will have its range of applicability extending from minus infinity to plus infinity. At this point, I like to remind you that x is equal to plus minus 1 are the removable singular point of Legendre differential equation. So, we generally apply Legendre differential equation in the range from minus 1 to plus 1, that is in between two regular points, and this matches with the fact that the angle theta is equal to 0 corresponds to this, and this corresponds to theta is equal to pi. In that case, it is the region where we should focus about the solution of this Hermite differential equation. Since x is equal to 0 is an ordinary point, we opt for the power series solution as y of x is equal to summation over k ranging from 0 to infinity ck x to the power k with c0 not equal to 0. If we differentiate this once and twice and put it in this equation, we get from this term k into k minus 1 x to the power k minus 2 minus twice alpha times or if we take these two on the other side, we get summation over k ck 2k minus alpha x to the power k, and here k ranges from 0 to infinity and k ranges from 0 to infinity. The recursion relation is obtained by equating the coefficient of x to the power k on either side of this. Since this is an identity, so this relation will valid for every value of x. That is to say, the coefficient of every power of x on the left will be equal to that on the right. So, x to the power k, this term contributes when it is k is replaced by k plus 2. So, this is k plus 2, this term is k plus 1 and this is k plus 2. Or where alpha is any real quantity, so if we want to find out the series solution, then there will be two solutions as for Legendre differential equation. One starting from C0, then going to C2, C3, etc. So we call it an even solution, which is comprising of C0, C2, x square, C4, x to the power 4 and going. And other one is starting from C1, and this gives you the odd solution, which is C1x, then C3 x cube, C5 x to the power 5 and so on and so forth. This is the even series and this is the odd series. Both the solutions are infinite series. So if we have infinite series solution, it is customary to check for its convergence. So we apply ratio test. So we apply ratio test for convergence. The statement is that uk plus 2 by uk, this is simply ck k plus 2 x to the power k plus 2 by ck x to the power k, which is ck plus 2 by ck x square. If we use this relation, then we get it as 2k minus alpha. In the denominator we have k plus 1 into k plus 2. This is for ck plus 2 by ck times x square. If we divide both numerator and denominator by k square, we get 2 by k minus alpha upon k square, and in the denominator it is 1 plus 1 upon k and 1 plus 2 upon k x square. As k tends to infinity, this is 1, so denominator is 1. In numerator, since alpha is any finite quantity, so alpha by k square goes to 0. So the time variation is limit. So we get limit k tends to infinity u k plus 2 by uk tending to this term twice x square by k. It may appear that the series is convergent, since as k increases, this falls off as 1 by k. In this point, we compare it with x to the power m e to the power x square, where m is any finite number. Then the this can be expanded in Taylor series as x to the power m summation over k is equal to 0 to infinity x to the power 2k by k factorial. If we take two consecutive terms of this series, the two consecutive terms of this series is x to the power m plus 2k plus 2 divided by k plus 1 factorial x to the power m plus 2k by k factorial. So this is equal to x square by k plus 1. As k tends to infinity, this variation is x square by k. So we know that the convergence or divergence of an infinite series cannot be altered by multiplying it by any finite number. So if we multiply it by 2, it matches with this variation. Since this function has asymptotic divergence, the infinite series solution of Hermite differential equation also have asymptotic divergence. So if as our region of interest is plus minus infinity, if it has to represent any physical quantity, then it should be finite asymptotically. It should be finite asymptotically, but it is found that the infinite series solution is not finite in asymptotic region. So the way out, what is the way out? The way out is here. Here we assume that alpha is any real quantity, and we found that for any real alpha value, both the solution of Hermite differential equation has asymptotic divergence. But if we choose some special values of alpha, say alpha is equal to 2n, where n is an integer, positive integer including non-negative integer. So if we choose alpha to be 2n, where n is non-negative integer, then we found that for even values of n, the even series becomes a polynomial, and for odd values of n, the odd series will become a polynomial. The other solution will remain infinite series and has asymptotic divergence. And the polynomial solution of Hermite differential equation is known as Hermite polynomial. That's why you will find in most of the books starts with this as Hermite differential equation. So we conclude that for any general value of alpha, both the for any real alpha for any real alpha, both the infinite series solutions diverge asymptotically. So we truncate the infinite series into a polynomial. So we choose alpha is equal to 2n, where n is equal to 0, 1, 2, etc. So as to truncate one of the solutions into a polynomial. This is known as Hermite polynomial. At this point, note that if alpha length, which is not equal to 2n, then the solution of this equation is Hermite. If we choose alpha is equal to 2n and the polynomial and is generally denoted as a chain of x. So we come to this relation with alpha is equal to 2n. So we have C k plus 2 is equal to, this is 2n and we write it as minus n minus k n minus k cn. Now we first try to develop the even series. The even series, so we start, the even series starts with C0 and go, then the next term is C2 involving C2, so we get for k is equal to 0, we get C2 is equal to minus 2 and 2n, this is 1 into 2 C0. For k is equal to 2, we have C4, this is minus 2 and this is n minus 2, 3 into 4 into C2, this is plus 2 square n into n minus 2, this is factorial 4 C0. For k is equal to 4, C6 is equal to n minus 4, 5 into 6 C4 is equal to minus 2 cube n into n minus 2 n minus 4 C0. So we can generalize C of 2k is equal to minus 1 to the power k, 2 to the power k, n minus 2 and we can write the even series as y even of x is equal to summation over k is equal to 0 to infinity c of 2k x to the power 2k, which is equal to this is the even series. Say n is equal to 2. If n happens to be 2, then only there will be C0 and C2 term, C4 onwards are 0. Similarly, if we set n is equal to 4, then there will be term involving C0, C2, C4, C6 onwards are 0. So, if n happens to be an even number, then the even series is a polynomial. So, for even n, y even is a polynomial of order n having n by 2 plus 1 number of terms. Just like that in the case of Legendre polynomial. For even n, y even is a polynomial, but y odd is an infinite series. Here, for even n, this is called the Hermite polynomial. Now come to the odd series. For k is equal to 1, we get C3 For k is equal to 1, we get C3 is equal to minus 2 and minus 1. This is 2 into 3, C1. For k is equal to 3, we get C5 minus 2 and minus 3. Then this is k is equal to 3, so this is 4 into 5, C3, so this is plus 2 square. Then n minus 1 and minus 3, then 5 factorial C1. We can generalize this as C of 2k plus 1 is equal to minus 1 to the power k. This is k plus 1 because this is plus, so in this case k is equal to 2 and this is 2 to the power k n minus 1 and minus 3, and going in this way n minus 2k minus 1. So this is basically equal to n minus 2k plus 1, and this thing is divided by 2k plus 1 factorial C of 1, and the corresponding odd series is y odd of x is equal to summation C of 2k plus 1 x to the power 2k plus 1, k ranges from 0 to infinity. So this is equal to summation you can take C1 out of the summation sign. This is the infinite odd series. If we put n is equal to 1, then C3 onwards are 0. There is only one term C1 x. If n is equal to 3, all the odd coefficients including C5 and highest are 0. So it will have only two terms. One is C1x, other one is C3x cube. So for odd values of n, the odd solution is a polynomial, while the even solution is an infinite series. So we see that if we choose a special value of alpha is equal to 2n, then one of the solution of the Hermite differential equation becomes a polynomial. And the polynomial, since it has finite number of terms and each term is finite, the resultant quantity is a finite, and it is called Hermite polynomial. Now we want to find out the expression for Hermite polynomial. So we see that in general the solution of Hermite differential equation comprises of two parts. One is which we call even. So first we derive the Hermite differential equation as minus 2x and the solution of y of x is equal to y even of x plus y odd of x. For n is equal to even, this is Hn of x. For n is equal to odd, this one is Hn of x. So our first objective is to find out an expression for the Hermite differential, Hermite polynomial. So we may say that the Hermite polynomial is one which satisfies this differential equation. Double prime stands for double derivative. This is the differential equation satisfied by a Hermite polynomial. Our is to find out the expression for the series expansion, the polynomial. So we rewrite the recursion relation. Our original recursion relation was ck plus 2 was minus 2 n minus k, k plus 1, k plus 2 ck. We write it as ck is equal to minus this is the relation. We just inverted the relation and we put for k is equal to n minus 2. So what do we get? We get k. This is minus n into n minus 1, the numerator, and denominator is 2, and from here we get 2 Cn. For k is equal to n minus 4, we get C of n minus 4, and in the denominator there is n minus 2 and n minus 3 term, minus n minus 2 and minus 3, and in the denominator we have 2 and this term is 4 C n minus 2. We replace Cn minus 2 in terms of Cn, so this sign is plus, and you will have n into n minus 1, n minus 2 and minus 3. In the denominator we have 1 2 from here and another 2 from here, so this is 2 square times 2 into 4 Cn. This can be written as n into n minus 1, n minus 2 and minus 3. This is 2 to the power 2 into 2 into 2 factorial times Cn. Similarly, we can write C of n minus 2k is equal to minus 1 to the power k. In the numerator we have n into n minus 1, n minus 2, and in the denominator this term will be 2 to the power 2k times k factorial Cn. This part can be written as n factorial, so the rest of the term is adjusted here, 2 to the power 2k, k factorial, and the rest part is n minus 2k factorial Cn. A popular choice of Cn is 2 to the power n. So this is where Cn is taken to be 2 to the power n. So we write Hermite polynomial Hn of x is equal to summation over k is equal to 0 to capital N C of n minus 2k x to the power n minus 2k. We write here, we have written the Hermite polynomial is a descending power series. You see the the power of x is n to the power n minus 2k, and this has the same power. So we write factorial then 2x n minus 2k, k factorial n minus 2k factorial. This is the Hermite polynomial, and n n is the number of terms, it is and this is n plus 1 by 2 for n is equal to odd. So we write Hermite polynomial as the series expansion for Hermite polynomial as Hn of x n factorial 2x to the power n minus 2k, and in the denominator it is k factorial n minus 2k factorial. Let us calculate few special Hermite polynomial using this expansion. First we put n is equal to 0 to get H0. So for H0 of x, so there is only one term corresponding to k is equal to 0, because n is equal to 0. If we put k to be 1, then this will be negative, and factorial of negative integer is not defined. So there will be a single term corresponding to k is equal to 0, and this is 0 factorial. This is 2x to the power 0, and in the denominator this is 0 factorial and 0 factorial. So this is simply 1. For h is equal to 1, h is equal to 1. So first term is k is equal to 0, k is equal, and if we put k is equal to 1, it is negative. So there will be again a single term, and this is for k is equal to 0. So this is 1 factorial 2x to the power 1, this is 0 factorial, and this is 1 factorial. So this is 2x. Coming to h2, there will be two terms, one corresponding to k is equal to 0, other one for k is equal to 1. When k is equal to 1, this is 0, and this part is 0, and for still higher values of k will make this negative, and hence not allowed. So there are two terms, one corresponding to k is equal to 0 term. So this is 2 factorial 2x to the power 2, 0 factorial 2 factorial. Then the second term minus, this is again 2 factorial, and this is 2x to the power 0, because k is equal to 1. So and this is 1 factorial 0 factorial. This goes, so this is 4x square from first term, and second term it is simply 2. So this is h2. Now as the last example, we consider h3 of x. First term is k is equal to 0, so this is 3 factorial 2x to the power 3, this is 0 factorial 3 factorial first term, minus second term k is equal to 1, if we put k is equal to 1, then this is n factorial, this is 2x to the power 1, then it is 1 factorial, and this is 3 minus 2, 1 factorial, and still higher values of k will make it negative, so there is no other term. So this is 8x cube, first term is 8x cube, and then this is factorial 3, 6 into 2, 12x. So in this way we can generate still higher order polynomials. For k n is equal to 4, there will be 3 terms. One is for k is equal to 1, this is 4 minus 2k. For n is equal to 4, this part is n minus 2k factorial. For k is equal to 0, it is 4 factorial. For k is equal to 1, it is 2 factorial. And for k is equal to 2, it is 0 factorial. Still higher are the values of k will make it negative. So there will be 3 terms. And we can find, one can find out this expression. The homework is that you put, so that the solution of y double prime minus twice xy prime plus 4y is equal to 0 is, this is H2, is y is equal to 4x square minus 2, apart from a constant. So that's all about today's class. Next day we shall consider Rodrigues formula. As we know that the Rodrigues formula is used to derive special function of a particular kind by repetitive differentiation of a known function.